I'll wait, I guess. Just send it. All right, so what we didn't talk about last time, but I just found it, is at the bottom of your notes from April 27th on electricity. Some stuff, but this is this important thing here. I don't know if this showed up on the test. We didn't talk about it, but it is like the governing, it's like Newton's laws for electricity. You know what I mean? It's like the most important thing.
Yeah.
The force between two or more charges, but you hopefully you're only dealing with two, where you got this thing, Q1, Q2 divided by the distance between them squared, where this is the picture. Pretty simple, actually. Q1, Q2, there's two charges, point charges, just like the point masses, like a car is just, I don't care, it's a car, it's a point mass. It has no volume, basically, right? And, you know, it has some charge equal to, well, it's going to be like 3 microcoulombs maybe, or something like that, right? And so once you understand this, you just plug these things in here, because you're going to be given that and that and that. You're going to be given all these things, and it's just a calculation. It's actually like, how good's your scientific notation? Because you're going to ask, what is this thing? Well, it's 9 with 9 zeros. So what is that? 9 times 10 to the 9th. And so you got to do, you know, let's do a quick example, actually. So if Q1 is 3, this is micro, so 10 to the negative 6th coulombs. That's the SI. It's always got to be an SI. So if you put in 3 here, you get a wrong answer. You better be 3 times 10 to the negative 6th. And with a distance of, you know, it doesn't really matter. Let's say, you know, 10 millimeters. And then milli is 10 to the negative 3. So 10 times 10 to the 3 meters. Straightforward, right?
Yeah.
Cool. Can do it real quick if you wish. I want to ask you, are these going to repel each other, or are they going to be attracted? So when you say they're sitting here, you let them go, are they going to move towards one another? Same force, so same length of arrows, actually, right? Or are they going to move away from each other? Like charges repel, opposites attract.
Are they going to attract?
Repel, because these are both positive quantities, right?
Oh, okay, yeah.
There's nothing there, they're positive numbers. So then you get, you know, whatever, 9 times 15. So 9 times 3 times 5 is, I don't know, 135, or just do it normally. Are you good with the scientific notation on your calculator?
Yeah.
Cool. So I don't know if you did it or whatever, but n squared, of course. Easy to make mistakes. Get that. Better square that. 10 answer negative 3 squared, something like 1350. Sounds good. And I doubt you're going to see any, if that probably wasn't even on the quiz, but just so you're prepared, or the test, it might be, but
okay.
It's not going to be any harder than that. I hope it shouldn't be. Okay, so there's that. Yeah, it looks like it's mostly going to focus on like this idea of the light bulb and current voltage and all of these ideas. I'll look at that other email too. Yeah, there was actually a lot here. I don't think we actually covered. But that's the basic thing. And then you get into there's your electricity pretest. And then if you have electricity activity, let's just look at it real quick. So electricity activity, number 1. Come on, you. That's good, I Yes. Prediction: when the two wires are placed on the light bulb will light up. Yeah, so remember we talked a lot about this. They have to be placed in the right way. The whole point is to complete the circuit.
Mhm.
Why? Because electrons need to flow. That's what current is. That's when you complete the circuit, you have current, you have electrons flowing, hence you have this light bulb lighting up. Yeah, let's talk about it. So battery, it's a chemical reaction in here to create, it literally fires electrons. Let's do it. So we got a battery, we got some wires, negative, positive, you might see that sometimes, but the little nub is always the positive.
Mhm.
Here's my beautiful light bulb. And let's make sure we're doing everything right. So it's your light bulb. There's this pretty specific thing here where one of them has to come out the side and the other has to go in or out the bottom, right? That was, I don't know if that was on your quiz, but like this would not produce a circuit simply because the metal contact is, one needs to be at the bottom, one needs to be at the side.
Mhm.
So electrons are going to flow this way. Why? Because we have positive. So whatever happens, chemical reaction, some acids, some bases, some reactions, and it literally just pushes electrons out of this positive end here. So electrons flow. What happens when electrons flow? We call that current. And that's how we get electricity. So enough electrons flow, enough electrons flow. If you don't have enough electrons, I don't know if you talk about this, but like your light bulb won't light up. Hence the voltage needs to be high enough. That's why you have to have a AA battery, and if you use a different
Mhm.
size battery that's less, well, you don't have enough voltage to push those electrons to power whatever it is you're powering. Anyways, so they come through here and then they go through the light bulb, and actually we can go even in depth, I think, because there was like this filament idea here that was like crown like that, and then you have the electrons keep going and they go up here along the metal. Remember we talked about conductance a lot, or rather conducting materials,
Mhm.
and this is literally the path. These blue arrows are the path that the electrons take. When the electrons flow, you have a current, you have complete circuit, you have electricity. Like that's like, I've said it 3 or 4 times, but that's why it's important, right?
Mhm.
You understand what I'm saying, then you understand this whole idea of electricity. And so this wire, this is a conducting metal. That's why it's copper or something, right? Because you have insulators. And you should know this idea as well. You do not have electricity with insulators because the electrons can't flow. They can't do anything. They can't go anywhere. So if you go, you had a sheet here. It's like, yeah, electricity activity number 2. Your prediction on some of these experiments, you got them all right. It's pretty straightforward to understand. Like, paper and plastic and pencil, wood, these are not going to conduct electricity because the electrons cannot complete the circuit. We had another diagram here, battery.
Mhm.
I'm going to just say everything again so it's just drilled into your mind. And you have the wires. Again, chemical reaction occurring. It pushes electrons out from the positive end always. So they flow away from the positive end. Wire, wire, wire. And then you have test material. This is what your experiment was. Okay, another wire. Hooray for us. It's got to go back. It's got to complete the circuit. But what happened was, you put a light bulb in here as well, right? There's a light bulb in series, we say, but that's
Mhm.
probably don't need that. But it's going to light up if this thing's a metal, because the electrons for metals, right? Conductors,
Mhm.
the E electrons flow to complete circuit. Remember how they get stuck in the material, basically. That's how you can think of it. So if this was wood, the electrons would get stuck here and they would not go this way, right? They would not flow to that negative end. They would not complete the circuit. That's why the light bulb doesn't light up. Why? Because this circuit is not complete. Electrons aren't flowing. You don't have current.
Okay.
And that's all of these things are that basic idea. Every single one of these electricity activities. Did you complete the circuit? The answer is yes. Okay, the light bulb's going to light up, and you got to get in here kind of crazy for some of these configurations, but just trace it. You got to remember the metal, the electrons flow on the metal. Why? Because it's a conductor. If the electrons flow and the circuit is complete, your light bulb's going to light up.
Okay.
So if we look at, I don't know, page number, the electricity activity number 5 here.
Okay.
With these weird configurations and stuff, you can see, okay, based on these things that we're talking about that you spent a couple weeks on, not only are the electrons flowing and like, okay, now you learned an extra thing. It has to go through the bottom and the side, because if it's not, then it's not going to flow, because the contacts are here. The metal contacts are here. Metal conducts electricity flow of electrons. But not only that, now you got the inside filament, which he taught you about. It's better flow along that or you're not going to get anything. That's electricity activity number 4. But then you put it all together, everything we've been talking about and all this stuff in electricity activity number 5. And that says, oh, look at your arrow. It's going through the positive end. Hooray, we know this well enough by now. And then the wire goes into the bottom of that first light bulb. I'm looking at the upper left diagram. See how the wire goes, and you have an arrow drawn there. And then your pencil markings, that's exactly what's happening. The electrons go through the bottom, up through the filament, and then it comes out the side. But guess what? That other light bulb is touching the side by side. And as long as that wire is out of the bottom of the second one, hey, complete circuit.
Mm-hmm.
But if the wire was coming out of the side of that second bottom bulb there, then according to what you're learning, the circuit would not be complete, even though all the metal's touching and all that, right?
Mm-hmm.
Okay, cool. So then, do the same thing for the other 2. Like when you're studying, just convince yourself, okay, trace the thing just like you did with the arrows. That's perfect. And it looks like that's going to light up. Oh, that's right. That first bulb is lit and those other 2 are not.
Mm-hmm.
And that's has to do with everything we're talking about. That one hanging off the right on the second upper right diagram makes sense. That it's not connected to the circuit. It's just touching that one point. It's got to be in the circuit because of those. That one's not even touching. But then the bottom one is like, well, they're both coming out the bottom, or one's coming out the side, the other's coming out the bottom. It's a dead end on that unlit one, right?
Okay, so it has to be the top and the side, or like one of those.
It has to be, for your light bulb to be lit, it's got to be one out the side and one out the bottom. So these are the possible configurations for lit. That's it. That's all you get for one light bulb. Of course, you can add a million light bulbs like they did, and then you got 2 touching. Okay, there it is. Or sorry, this one, and then it comes in the bottom here, but it still goes through this whole thing. And as long as it comes out the side, okay, yeah, right. You just have to trace. So it's coming in the bottom, but then remember, okay, it came in the bottom. That means it better come out of one of these sides. And it looks like, oh, it's touching that one. And then it comes into the side of that one. So then guess what? It better come out the bottom there. I'm looking at that first upper left diagram on electricity 5 for this one here. Does that make sense?
Sorry, can you explain that again? It cut out.
So the wires, let's start over. Let me finish this thought. So this is what you got here. We're going to assume the battery's fine. So the guy's coming in, we see the thing coming in the bottom here.
Mm-hmm.
Well, this is what I was talking about up here. Well, if one's coming in the bottom, it better come out of the side if we want it to be complete, right?
Okay.
And so we see that, oh, it does technically, the circuit follows out of the side simply because it's touching this contact here in the other light bulb.
Mhm.
That's why it works. And then guess what? Oh, this one's coming into the side of that one. Well, it better go out of the bottom because these are the only lit configurations. One side, one bottom. Can't have two sides. And so
Okay.
this better come out the bottom to complete the circuit for them both to be lit.
Okay.
So use these diagrams and practice that to get that going on all these.
Okay.
So I kind of skipped through it before, but that's what you've got like 6 activities. We didn't talk about the 6th one for some reason. I think we got cut short, but there's these 5 activities like, oh, light bulb, battery, circuit, complete the circuit. That's like activity 1, right? And then in activity 2 and kind of 3, you learn, oh, well, now it better be connected in the bottom and the side. Side does not work. Wrong. And then electricity activity 4 and 5, you start seeing, oh, now it's going through the filament inside the bulb, right?
Mhm.
So it's all these things you talked about, just putting it all together though. See what I'm saying?
Yeah.
And so 5 and 6 are like the culmination of all the ones before. So, you know, you have to understand 1 through 4 to understand 5 and 6.
Okay.
But I think you do, hopefully, because you said it went well before, and it's not that difficult, but and I think you were comfortable with it before. If you aren't now, also, I'm not sure.
Mhm.
So if I got it coming in the side, well, you know, better come out of the bottom. Or if it's coming in the bottom, well, it better come out of one of the sides. Yeah.
Yeah.
Comes in the side and you got that thing, well, it's not going to work. But then you take that extra idea to activity 5 and you say, oh, now I got 2 bulbs touching. That's what I was talking about here. Let's do it one more time. And so you got your wire coming in. Oh, okay. And then it comes in the bottom, I believe. So based on what you just said, well, it can't come out. It has to come out of one of the sides. It can't come back out the bottom. And you say, okay, well, there's another bulb touching here, so it must come out of the side there.
Mhm.
And so, in fact, let me even be a little bit better here. It comes in the bottom and then it goes through the filament, right? That's really what's happening. Well, it better come out of that one of those sides, but it happens to be this side because it's already touching a bulb. It comes
Yeah.
in here and then it's got to go through the filament again. But remember, if it came in the side, it better come out the bottom. And that's why these things can be lit on electricity activity number 5. Like if you understand that one, you have a good chance of one. That's the base case. You know what I mean? That's the basic example.
Okay.
Yeah. And like I said, electricity activity 4 is just, okay, it's going to go through the filament now. Light bulbs have internal parts that complete a circuit. So it has to go through the filament. It doesn't go through the air. You know, if we have a light bulb,
Yeah.
filament. Okay, let's go in the side. Well, the electrons are going to go this way. They have to go through the filament. And if we're going out the side, better come out the bottom. That's what we learned before.
Mhm.
And it's not going to go like this. Like this is not the path. This is definitely not the path. You know, well, I think I'll go over
Yeah.
here and
Okay.
over here, maybe. And then out the side, you already know, hopefully. It has to follow the metal because air is an insulator. We talked that a little bit. You know, it's not going to go like this all the way around. Nope. Right?
Yeah.
Okay. The electrons have to follow the path of the metal, the wire. And the filament is just the wire inside the light bulb, but it's just a wire. You can think of it all as the same. And the battery is basically just one big wire as far as you're concerned.
Yeah. Okay.
Where electrons come out of the positive end or the nub on your diagrams.
Okay.
And so there's like a blank page that doesn't have anything, and there's 4 configurations on there, and we're doing it again. We're saying follow the path of the electron.
Mhm.
Like that upper left one, the bottoms are touching. It comes in the side on the first one, then it goes out the bottom, comes in the bottom on the second one, so it better go out the side. So that means they're both lit, as you correctly identified, it looks like.
Okay.
But then the second one, they're both unlit. Why? Because side are touching. If one's coming inside, it better come out the bottom, right?
Yeah.
Okay. Have we driven it into the ground enough? You think you got it?
Yeah, I think I understand.
Okay, good. Yeah, that's important because that's most of this email here. I mean, this it's all about these light bulbs. You
Yeah.
got the electricity pretest, which we can talk about right now too. Let me just check what you got, what you sent. Cycling fan with no lights. It's hard to read that. Yeah, he's like an engineer or something. I think we deducted that before.
Yeah,
Or
it's very weird.
Or like then it's like, well, wait a minute. If he's an engineer, what's he doing? Not that it's nothing wrong with it. It's just like, that's kind of a downgrade. No
Yeah.
offense to him or anything, but all right, that's
Yeah.
the math. Okay, well, I'm gonna look at the electricity pretest. I remember we ran through this pretty quickly before, but we can talk about each little point if you want.
Okay.
And so electricity pretest is what I'm looking at. Volts are what injure or kill people. This thing is current. We call it current. That's electrons actually flowing, right? So you need a high current to get hurt. Number two is the similar charges are attracted. Nope, right? Opposites attract. So better be a positive and a negative. Otherwise, every other combination repels. Positive, positive, negative, negative. There's only 3 combinations, right? The little shocks you receive, grabbing a doorknob, static electricity. Electrons have built up on this doorknob. And I remember us talking about the gas. I was thinking about us talking about that when I was getting gas the other day. I'm like, oh, better touch this metal here.
Yeah.
Don't know, ignite the fumes. But yeah, when there's excess electrons, i.e. too many electrons that can be held on the body, that's when you have static electricity.
Yeah. Okay.
Like the balloon, rubbing the balloon on the carpet, you're literally ripping electrons away from the carpet. Or remember I think we talked about when you slide out of your car and like it can be a little staticky sometimes or whatever, you're literally
Yeah.
taking electrons from the seat. And that extra buildup of electrons is static electricity. That's why there's a discharge. That's why there's the little shocks you receive. They're electrons going to your body because you can take a lot more than the little doorknob or whatever. You know what I mean?
Yes.
Lightning never strikes the same place twice. Yes, one guy got struck 7 times. I guess it wasn't the same place, but yeah, it doesn't matter. Batteries, yeah, chemical reaction for the battery. That's good. We talked about. They die when they run out of electricity. Sure, I don't know what that means. They produce electricity. It's fun. Yeah, the cell phone with the gas tank thing. It's the sparks. That's what we talked about. Oh yeah, one of the cool things is they're sitting in a vehicle. You're in a metal cage. The car is a cage because it's enclosed, right? And it's metal for the most part. And you sit inside of it, and as long as you're not touching something that's attached to the cage or the car, the outside of the car, it's not going to get inside you for that same damn reason about the light bulbs. It's air, is insulator, and there's chairs which are definitely an insulator. These cushy chairs, like the electrons. I don't care how many electrons are, like an lightning strike, they still have to flow through the metal. That's why you're safe in a car or in an electric cage.
Okay.
There's a pretty cool thing if you get a chance. I guess I could bring it up, but Faraday's cage. It's like a pretty badass YouTube video where a guy stands in a cage and he gets like the equivalent of like 10 lightning strikes shot at him, but he's
Oh my
fine
gosh.
because he's in that metal cage. And it's just,
Yeah.
I mean, you spend like a quarter of a class, trying to understand this in college upper division physics, but it's pretty cool.
Yeah.
Like what's actually happening. Okay, so vehicle, we did that. Okay. Yeah, I think you're good. You can read this stuff. If that was even on the test, I don't know. All right, so I'm gonna look at what you sent on the other one. Their notes. Doesn't look like there's any math or anything.
Yeah, there's no math this unit.
Okay, so maybe if you have it in front of you, I don't know if I'm gonna be right, but I'll try to like say, okay, this is like the most important thing, I guess. know this guy a little bit, and based on the physics, like Ohm's law, you should put a star next to Ohm's law. That's actually the first thing we talked about before. I don't know if he's going to have it, but there's that current. Current equals voltage divided by resistance. Current is I, V over R. It's the line, that equation in words just below Ohm's law. Current equals voltage / resistance.
Mhm.
I told you it's V equals IR. Well, you can hopefully solve for V, multiply both sides by R, and you get V equals IR, right? But that there's going to be something on this, like a qualitative, like, what is Ohm's law? You know,
Yeah.
like start by that for sure. The current that moves through a conductor is directly proportional. So those words are saying, okay, here, you know, inversely proportional to resistance. It's just saying the equation in words, right? And hopefully you're
Mhm.
good with proportionality from math. I skipped the above stuff because it's kind of hard to read also, but also it doesn't seem important. Does it say cycling fan or circling fan? Ceiling
Um,
fans, ceiling fan.
oh yeah, ceiling fan. My pen was like giving out.
Yeah, ceiling fan with no lights, extra wire gets a wire, but green to green or naked, wire to white, black. Okay, so, you know, match the colors to your ceiling fan. Or it doesn't really matter if it's a ceiling fan or not, you know, it's pretty much, I mean, it could be useful if you're gonna, you know, installing, usually you pay an electrician to do that, but
Yeah.
whatever. Match the colors if you're gonna install something is the moral of this story, like the first 5 lines, I guess. I would not put a star by that.
Yeah.
unless he said like, I'm obsessed with ceiling fans and this is gonna be on the test.
Yeah. He spent
All
like
right.
the first half of class talking about it. So
Oh
it's like
man,
it's weird.
yeah, that's a little weird. That's a little, dude, you're a little sus on that, man. What are you doing with those fans? It's a little, I don't
Yeah.
know, man. Half a
Yeah.
class on this. I'll give you 5 minutes, dude, and then you got to move on. Fetish boy
Yeah.
with the ceiling fans.
Yeah.
All right, so we got below Ohm's law. This is pretty important, I guess. At least objectively, direct current, alternating current. These are 2 types of current. It's pretty straightforward. Like direct current, the electrons just continually flow, basically the same magnitude with the same direction for sure. The direction is the most important part. And then
Mhm.
alternating, they go back and forth, right? And I don't know if you might have heard this, but all the electrical outlets are alternating current AC. That's what that means, right?
Yeah.
Actually, AC/DC, I believe they got their name from that, which is an interesting trivia. See, that's what he should be saying, but like just mention it and then move on. But he would probably say the lead singer died in 1982 or whatever, like going crazy with
Yeah.
this.
We did talk about that a little bit.
All right. So I think, I mean, I said what I need to say. I mean, alternates direction, alternating current, AC, right? Um,
Mhm.
Here you go. The USA. Any numbers? I would say maybe not a star, like a star, but like, okay, USA has the electricity comes out of your walls, basically alternates 60 times per second. Could be a little multiple choice. I don't know.
Mhm.
Frequency. Have you learned about frequency before from, I don't think we did that really in physics. I don't know. We didn't meet that often, but frequency is literally how frequent does it change, right? Like hertz is like an inverse time period. So it does, you know, 60 times per second. So it kind of, hopefully it kind of brings it together, I guess.
Mhm.
Yeah, it is kind of interesting for some people. It is actually interesting. Like the electricity before it gets to your house, I don't know where it happens, but it is actually direct current. And then the transformers, maybe the box on your house, like switches it to alternating current because you can't handle, like if you do get shocked with direct current, it grabs you because it moves in one direction. Whereas like alternating current, you can just, you jump out. I don't know if you've ever been shocked, but you jump away and it hurts obviously. But if it's direct
Oh,
current, it sucks you in, like you get stuck to it actually, depending on how big the current is. So like
my
people,
gosh.
yeah, no, that's what, so they actually have to change it from direct current to alternating current, like on the house. And that's why. Okay. And then the last one, 513, and that's the last lecture. So you said you got a test tomorrow. What is tomorrow? Wednesday? And
Mhm.
then your finals are the next week, right?
Yes, my finals on Monday.
Oh, okay. Nice. So electricity is the orderly flow of electrons. We've hopefully drilled that into your head. In order for the
Mhm.
charge to flow, what is needed is a complete circuit. There you go. Is a circuit, complete circuit. A voltage. Yeah, sure. Yeah, there you go. Getting a little more physicsy, but difference in electric potential. I wouldn't worry about that. I doubt he's gonna be too obsessed with the fans and all this stuff. So
Yeah.
but that's, if you can remember that about the voltage, it's like don't remember the difference in electric potential, even though that's literally what it is and like what you would learn at college level physics. It's just, it seems too much for where you are now. But the push, it, remember I was saying it pushes the electrons. That's what that voltage is for the battery. And I think you're good if you just kind of remember that. It's a measure of potential exists for current to flow. That's what we talked about. Voltage is directly related to the current, and look at that equation, V I or whatever, I equals V over R. If you have a larger voltage, then you have a larger current. Why? Because
Mhm.
that voltage pushes the electrons. So if you have a higher voltage, you can push more electrons, or you can push the same amount of electrons faster to get a larger current. So, and then I would, because we know our boy here, I would take a look at these numbers here on current, like, what is that? 1 milliamp, 0.001 amp is a throbbing tingle. maybe remember that phrase. I don't know. 0.005 amps is painful. Like I would take a minute, I guess, on that, just because we know he's weird. And if he took the time, I guess, to write these down, 0.07 amps is possibly fatal. And if you, I mean, what is that? That's like 6 things to remember. I would remember, like, definitely the amps is virtually always fatal. 0.1 amps, right? A tenth of an amp. That is pretty big.
Mhm.
And remember, and then pick, maybe the first one, throbbing tingle, or like, don't remember, try to remember them all. But I would remember at least the last one or the first one if you can.
Okay.
And then you got your resistance. So these three things, voltage, current, resistance, they make up electricity, kind of. And we spend some good time talking about it. It sounds like you understand it. So if you like understand kind of all this stuff about the light bulbs, it's the same, even though it seems different because we're talking about words and more abstractly current, electrons moving, and voltage. Like, that's literally what's happening through these light bulb experiments. Pushing electrons. Oh yeah, pushing electrons is a current. How do we do that? Well, it's attached to a battery. What? The battery has voltage and it pushes the electrons, creating a current. The light bulb is the resistance.
Mhm.
So, resistance, opposition to the flow of current, hence the word, right? Resistance slows down the flow of current, and everything is a resistor. That's, yeah. And there you go. Something causes a little resistance, some cause more than others. So if a resistance slows down the flow of current, your words there, which, I agree with that. Something causes a little resistance. Guess what we call those things? Conductors, because there's little resistance, so the electrons can flow more easily. They conduct electricity better.
Mhm.
Some cause more than others, more resistance than others. We call them insulators, because it resists the flow of electrons more than others. And if resistance slows down the flow of current, right? And hopefully that brings you all back to the beginning, basically. And hopefully that brings it
Yeah.
full circle. Because that's the end there. That's the last page of that. And let me write this down for you. So hopefully you wrote down the things I said, like Ohm's law and star, and remember those stupid things. Point tenth of an amp is virtually always fatal, but this brings it full circle for you right here.
Mhm.
So voltage pushes electrons. Voltage that pushes electrons. Oh yeah, this is the battery. Current is literally flow of electrons. And I mean, just see above. If you understand the voltage, everything there, then you kind of can understand the current, I guess. And then this is not, it's not the actual wire, but it's what, at least when you have a lab and you're using your light bulbs and stuff, the battery is the voltage. You have to have three things. Battery is the voltage, the light bulb is the resistor or the resistance, the thing that is resisting the flow of current. And then the current is kind of the wires, right? Even though the wire is technically the conductor that through which the electrons flow or some BS like that, like you can think of it as the wire. Like this is the wire. And you're, you know, pay attention and be like, well, it's not really that, but the electrons move through the wire because current is actually electrons moving. So just be careful. Don't take it literally, kind of. But okay, when it's slows down flow of current, that's pretty good. Slows down current, which is the flow of the electrons or the flow of current, whatever, it's all the same thing. And this is the light bulb. Or the material that you were testing, right? Like that key or something that's super metallic that does light up the light bulb. If you go back to your paper clip or your key, it's like that's still a resistor. It just flows it just resists the flow of electrons very little. But it's kind of like Newton's law. Like there's always friction or there's always air resistance, but we don't really acknowledge it because it's way too complex. You know, you got to go to graduate school truly or an engineering degree in depth to actually understand how much and to what effect, right? So it's like we don't care, and it's very small anyways usually. But the key, any metallic, any just the same idea as projectile motion. There's always air resistance. There's always some resistance, but when you have a metal, it's just negligible. It's so little that we don't really care.
Mhm.
But then when you go and some things cause little resistance, so you can say like, you know, little cause little resistance. This is exactly what we're talking about, and these are the conductors because they conduct electricity.
Mhm.
Resistance. Conductors. I just want to finish this, and this is pretty much it, unless I can have some questions. What is it? More resistance, whatever. And then these are the insulators. So hopefully this page and everything we talked about kind of brings it full circle back to your first thing when you first learned about these light bulbs and this stuff and whatever. So is there anything like sticking in your mind specifically you want to ask about any of this?
Not really. This is starting to make a lot more sense.
Okay. But yeah, it's honestly, this is probably too much information than what you need. I hope it should be, honestly. And but we know this guy's kind of a little crazy, so maybe he's really gonna do some of this stupid stuff on the test. Hopefully not. You said the tests are usually pretty reasonable, right?
Yeah, usually.
That's good. He's not completely crazy then.
Yeah.
All right. Do you have, this is everything from these things, right? All the notes and everything that you've taken.
Yeah. Oh, I have I found another like worksheet. Do you want me to send that?
Yeah, sure. I also found electricity activity 6, which we never really talked about. It's all the same,
Okay.
but like if you want to, or send what you got, if it's kind of new, or if you think we should, I guess I should at least look at it.
Yeah, I'll send it to you and we'll see.
Okay.
Okay.
I just want to mention it briefly. If you look at electricity activity 1 and electricity activity 6, basically the first and last activities, you got the black and the red wires. And the point is the black ones should always go to the positives. If you want to connect something in a circuit, that's why you have your black wire go into the nub or the positive end of the battery, right? And then when it's on the light bulb, notice there's no indicator for positive because it doesn't matter. It just needs to go through the circuit. And in truth, you can put the red at the positive. It doesn't matter. It's just a convention, right? It's really for people like electricians to say, oh, how is this set up so I know how to fix it? You know what I mean? But
Yeah.
a wire is a wire. I don't care what color it is. You know what I mean? So that's a little tidbit for you. All right, let me look what you did. Oh, here you go. Oh, there's 10 of them. Okay, there you go. Yeah, I don't have 7 and 8, but maybe that's all right. Oh yeah, these FET things. Did you do the FET, Colorado?
Yes.
Yeah, cool. Build a simple circuit. And did it go well?
Yes.
Yeah, those are pretty helpful, honestly, at least when I used to do them. And they can be dry and boring, but they are actually pretty good for learning. Insert a resistor. There you go. And yeah, I mean, what you wrote down here is literally perfect. I don't know if you got it from class, but like, that's what you want to say and think about. The effect from the resistor is that the electrons move more slowly at a slower rate. The bulb is not as bright. If you have a larger bulb or a larger resistor, it might still light up, but it won't be as bright. Why? Because less electrons can flow through that circuit. More of them get stuck in there if you have more resistance, remember?
Yeah.
When the bulb and resistors are moved. There you go. Nice, good. This is exactly what we were talking about here before, and hopefully, I mean, this is, yeah, that makes sense. And that, I think on 10, you start talking about open circuits, or no, that was number 6. So open circuit is like there's nothing in it, which is the third question on your electricity activity number 9. When the bulb and the resistor and the light bulb from this, whatever, they're removed and you just have these wires. So the battery is short circuited basically. Why? Because the positive end of the battery is just connected to the negative end. Hence, too many electrons are moving, and sure, the battery can light on fire, but all that is fine to think about. Oh yeah, here you go. Yeah, so hopefully, maybe you wouldn't get the words in the exact order, but hopefully you can understand the reason why the bulb is brighter if you add 2 batteries than it is 1. And the bulb's going to be way brighter if you add 10 batteries than 1 or 2 or 9 batteries, right? It's the voltage. 2 batteries, twice the voltage. What does voltage do? It pushes the electrons more with more force, literally. And so what happens when the electrons move faster? Well, there's a larger current. So the bulb is definitely going to be brighter, right?
Yes.
And yeah, that's fine. More voltage equals more speed, pushes the electrons faster. That's the most correct thing you can think about. Because you're talking about speed. Speed of what? Well, the speed of the electrons moving. Why? Because the flow of electrons is electricity.
Okay.
And then we got AC, DC, AC, DC, and DC is an electric charge that moves in one direction. Yeah. So DC direct current, whatever, is one directional. And then AC alternate, right? It alternates direction. That's fairly straightforward. And here you go. I mean, which makes the bulb flicker under an alternating current, I guess. I don't know. We'd have to go to that thing, but I wouldn't worry about it too much because obviously all your bulbs are going through alternating current, but it's literally alternating so fast. 60 times per second isn't that fast, but it's fast enough, right? So you don't notice the flicker, I guess.
Mhm.
Like obviously your lights aren't flickering unless they're going to go out there. They do flicker sometimes, and then that means there's something going on with the system. Maybe the electrons aren't going as fast. I don't honestly know enough about that, but I'm looking at observation 1, and the electrons are moving back and forth, which makes the light bulb flicker, but they got to be moving back and forth slow enough, right? I think is the point I was trying to make. Between these alternating directions rather than moving one full direction. Makes sense. Great. Yeah, so that whole page, DC, AC, you got that. One direction, alternating. I would remember that little thing. I think maybe if you can, that the AC in the United States, it flows like it alternates 60 times per second. So
Okay.
yeah, that's the pages. We didn't look at 7 and 8, but maybe you don't have them or they're not that important. I don't know. We are meeting again here in an hour. I don't know if you wanted to do a review of the whole thing or math or what. So
I don't know. I'm gonna look at number 7 and 8,
okay.
and I'll see if we need to look over this.
Well, yeah, if you don't have anything else, then yeah, mine as well.
Okay.
So yeah, I'll see you. I'll talk to you in 10 minutes.
Okay. Bye.
Bye.